So, good evening everyone. I think no one is here. So, okay, let's start. Today I am gonna present some more concepts and questions based on reactive intermediate carbenes and nitrene. So, I will continue my session from the last week. So, if you guys have remembered, I gave two tasks to you guys that both are based on previous week's problems, different kind of. So one was this one. So I just gave this reaction, like for this substrate, if we apply H if we apply light, what will be happen? So you can see this is the answer. So I don't know if you guys have tried or not. If you have tried, then very good. So here you can see after application of light, this N2 will eliminate from the system, generating a carbene system, as you have learned before. So the carbene system will generate, and this carbene will add to this double bond, like addition reaction. You have learned last week, and Professor Shamanta has also taught you all these things, that this carbene will add to this double bond and giving us this type of cyclopropane ring. This you see here, the new cyclopropane ring has been generated. A new cyclopropane ring has generated. You can see. So this was our first task to you guys, and this was the second one. I asked if you can suggest a mechanism from this to this. This is the alkynyl carbene. I discussed about this last session. If some of you haven't watched that session, then you guys can go to the, I think that has been uploaded by the NPTEL. So this is also has been uploaded in the YouTube also. The channel name is Chanda Devnath PMRF NPTEL TAship. If you want to watch that video again or that class again, there I have discussed some more problems regarding this. You can go through that, and that will give you a basic idea of carbene. So today I am also discussing some more problems and questions based on this concept. So in the last session I asked that what if this is not here, this is the alkynyl carbene. So I just asked a normal chemistry question, that if you guys can think about what is the mechanism from here to here, how this is generating. I don't know if you guys have solved or not. For those who have tried but it was not, and who have tried just to check that it was right or not, I just gave the answer here. So this is the mechanism. See here, as is all of you may know that butyl lithium is a strong base. So butyl lithium will deprotonate this reagent and giving us this reagent. See, a negative charge which generate. So we all know that carbonyl compound is a high electrophilic center. So when this nucleophile will generate, it will attack to this carbonyl carbon, giving us this type of O- ion, and this type of system intermediate will generate. So if you guys have heard or learned about the Peterson olefination, so similarly this will be like this O- will generate, and we all know that silicon has a vacant d orbital. So O minus will donate its electron to the silicon, giving is this type of 4-member cyclic intermediate, and this will eliminate, sorry, so this won't be N2, sorry, this won't be N2, this is not N2, N2 will eliminate in this step, N2 will, sorry, I just did the mistake, N2 will eliminate in this step, here N2 will eliminate in this step, here only this will eliminate like this, it will go here, and this bond will go here. In this way, this is called Peterson olefination. Why olefination? Because olefin is getting generated. So this type of olefin will generate, and in a similar way, when because of and this N2 will eliminate and giving us this type of alkynyl carbene intermediate. Then CH insertion is happening that I discussed in the last week. So this is the answer. So this is normal chemistry question just to get a idea or just to think about this some normal reaction. I just asked this question because just based on carbene you will not get some questions. Some questions will be there which are related to carbene, but one step will be some not just basic concept of chemistry. Some steps will be from the basic concept. Then in the second step maybe the carbene is getting involved. So here everyone, I think this is clear now. So then move, I just get move. So whoever has completed or tried this reaction is like all the best. Whoever got this answer is correct, and all the best. So let's go to the addition reaction. I just see once it's getting recorded or not. 1 second. Just okay. I was just checking it's getting recorded or not. Okay. Then let's come to the addition reaction of carbene. This I discussed last week. So today I am just giving you some more examples based on this. So it will give you an idea of this addition reaction in a wider aspect. So here you can see. So here you can see this is a E double bond. There is a E double bond. So when this is a diazocarbonyl compound, I discussed about this in the last week. So here after N2 elimination, a carbene will generate. So this carbene will add it. This carbene will add to this double bond, giving us this compound. So it is highly stereospecific and giving us so here from E we are getting exo product, and if you take Z alkene, then we would get endo product. So it is highly stereospecific because we know that in this process when N2 is getting eliminated, the carbene generated is a singlet carbene most of the cases. So from the stereospecificity also we can conclude that the carbene generated here is a singlet carbene because the product is highly stereospecific, and so from E on we are only getting exo product, and if we would take Z then we would get endo product. And another concept about this is so here there is a fused 5 and 5 and 3 member ring is getting formed bicyclic. So here I have shown another similar kind of reaction where there after this N2 elimination, carbene will get generated, which will be added to this double bond, giving us this cyclopropane ring, which will in the by further steps which can be transformed into this natural compound, which can be in further modification by applying some more reactions and methodologies, we can get this natural product. This is also very stereoselective. See here, this bond is forming from the this cyclopropane ring is forming above the ring. So this is also highly stereoselective. So the next reaction is this one. So this is the same kind of reaction as I am discussing, addition reaction. Here also this is diazocarbonyl compound, N2 will eliminate as like before, and this carbene, generated carbene will added to this double bond. Will be added to this double bond. Why this double bond? If you guys can say that as I have discussed before also, that this addition reaction prefers the electron rich double bond in the previous session. You can check there also that addition reaction always prefers the electron rich double bond. So here you can see there is a ester group which is connected to this double bond directly. So as per according to our basic knowledge, we know that ester group has a minus R and minus I effect, that is inductive effect or and resonance effect. So this double bond get delocalized through this ester group. So if we may think that this is highly electron deficient. So why this carbene is reacting with this double bond, not with this double bond? Because here the ester group is not directly connected to this double bond. But the thing is, you can see here the double bond is connected to only one alkyl group. But here the double bond is connected with two alkyl groups. So we also know that alkyl group has a plus I effect. Alkyl group has a plus I effect. So maybe here the plus I effect of two alkyl group is enough to compensate the electron withdrawing effect of the carbon ester group. And here also another reason is there, when this carbene is getting added to this double bond, a higher member ring will form. We can count that 1, 2, 3, 4, 7. A 7-member ring will form, 7-3 fused. If it added to this double bond, a 7-3 fused ring would form. A 7-3 fused ring would form, which is, as you know, 3 and 7 both are not that much stable. So this double bond, instead of being being in a distance with this ester group, this won't react because it will give a 7-3 fused ring, and also this has some two alkyl groups. So this double bond is kind of electron rich to react with this carbene system and giving us this type of 5-3 fused bicyclic ring. 5-3 fused bicyclic. Why 5-3? See, this is a 5-member ring and this is a 3-member ring. We are getting a 5-3 fused bicyclic compound. So if we hit this from here to here, the carbene reaction is happening. So now if we heat the compound again with the 580 degrees Celsius, if we heat the compound again, so what we will get here? See how this product is getting generated. And if you guys can think, I am giving 1 minute, just think once that how this product is getting generated. See, I have written here also, you can notice. So think once how this product is getting generated. So I think most of you has have heard about the cope rearrangement. So what that is a 3-3 sigma topic rearrangement. This cope rearrangement, what is called also called, this is the name reaction. The mechanism that is mainly based on 3-3 sigma topic rearrangement. 3-3 sigma topic rearrangement. So what is happening in case of, so you may think that we all know that the the initial structure for the 3-3 sigma topic rearrangement is a diene complex. This type of moiety usually reacts in a 3-3 sigma topic rearrangement. You guys have, so this type of substrate react. So here we how we count 1. So what is happening if we heat this compound? This shift here. This is a concerted mechanism. Every bond is forming and breaking in a single step. So giving us this compound. See? So here this bond is, so here this bond is getting broken and this bond is forming new. So this is called 3-3 sigmatropic 3-3 sigmatropic reaction. So, so if you think that here this type of system is not there, then why I am saying that here 3-3 sigmatropic reaction is happening, the cope rearrangement is happening. So in your prior, when you were in your prior classes, you may have learned that a triple bond also acts as a double bond. A triple bond also acts as an alkene system because of the close overlapping of the p orbital. So this triple bond may also act as a double bond. So if we consider this as a double bond, so the similar kind of systems you can find. See, you consider it as a double bond, then what will happen? This will be 1. Sorry. Here this is not actually sigmatropic. Normal reaction is happening. I just missed the normal reaction is happening. Just not say here. This is going here, attacking this position, and kind of normal reaction here is not sigmatropic. Sorry, this sigmatropic side. Sorry, and see that this double bond is getting broken here and is getting here. So we are getting this type of sigma reaction here. So the next reaction is this type of reaction is our carbene system can be generated from halo mercury compound also. That from mercury compound also we can get this type of carbene. We can generate the carbene. So here you can see here is a mercury compound. It will generate a carbene. This CO2 and Br. This one here will remove to generate the carbene. So this is our carbene. So this will add to this double bond, giving us, as this is a giving us this compound. So it can add in this way, and so total is this 50%. We will get two product here. So this is another reaction of halomercurial reaction, where similarly again a carbene system will generate. See here again a carbene system will generate, which will add to this double bond, giving this compound. So there is a printing mistake, I think. It will be, both will be CF3. Both will be CF3. Both will be CF3. As you can see that here both are CF3. So we will get this compound. It's simple. The carbene will generate, which will add to this double bond. So this next is the reactions of carbene generated by alpha elimination. You have all read about the alpha elimination. Professor has also taught you, and in the last session I have also discussed some reaction based on the alpha elimination. So here the carbene will generate through alpha elimination. So when this butyl lithium is a base, when butyl lithium will be added, first one, you know the mechanism, first one proton will be deprotonate, and then one bromine will be removed, and it will generate a carbene system. For those who haven't seen the last video, I'm just explaining again. So this is our system. So a negative will generate after the base react with it. So a negative will generate. This butyl lithium will deprotonate one proton from here, giving us this, So giving us this. Then again one bromine will get eliminated, giving us the carbene, our expected carbene compound. Sorry, because I don't have pen. So this carbene will generate it, and it will add up to this double bond, giving us this compound. Again another reaction is there, where butyl lithium will be added, and butyl lithium will take one bromine from here, another bromine will also, we all know that butyl can attack bromine ion also. So this is bit different from the normal alpha elimination you have seen till now. More normally we have seen that the base deprotonate one proton. The base will take one proton first, then it will alpha eliminate another halogen atom. But here you can see there is no hydrogen is here. So what is happening here? This type of compound is here. One fluorine, three bromine atom. So butyl lithium will take up butyl lithium is a negative charge. So butyl lithium will take one bromine from here and generate a negative here, and again another bromine will eliminate, giving us another bromine will eliminate as alpha elimination, and giving us this type of carbene, which will add to this double bond, giving us this compound. So the carbene is here, this one bromine, one fluorine. So you may some of you may think that why butyl bromine is also a halogen, fluorine is also a halogen. So why butyl lithium is taking the bromine atom? So simple thing that the carbon bromine bond is weaker than that of the carbon fluorine bond, because there is a 2p overlap, and while in case of bromine atom there is a 2p 4p overlap. Because of that the carbon bromine bond is weaker, so this will be broken faster than that of the carbon fluorine bond. So here I have shown another example where there is a by application of base, this carbene will generate. This is so by application of base from chloroform. This one we have wrote that from chloroform we will get this carbene. It is chlorine. Sorry, we will get this carbene. So this carbene here, one double bond is there. So this carbene will add up from here, from here. Attack from here and giving us this type of cyclic compound. So let's move to the next. Everyone has just, you can note down this if anyone is following up this video, so we can note down this question. So this may help you to get a idea about the carbene reaction. So our next is this one. This is also, so I have shown the product. This concept I have discussed earlier also. We all know this is this type of this is a Simon-Smith reagent. You may have remembered this is a Simon-Smith reagent. So in case of Simon-Smith reagent, when zinc is there, zinc is a highly coordinating metal. So it will coordinate with the adjacent wedge bond. So as it will coordinate with the wedge bond, so as the wedge group is below the plane, so because of this zinc coordination with this wedge, the ring will form, the cyclopropane ring will also form below the ring. Instead of the presence of this methyl group below the ring, this coordination is such effective that the bulkiness of methyl group can be eliminated. So our next reaction is this one. Here also, because of this OH group, the ring is forming below the plane, and this, as it is forming below the plane, automatically the OMe will go above the plane. So our next reaction is this one. So we all know by the application of rhodium plus 2 catalyst, a carbene will generate. So if I draw the, so by the application of I'm just writing as this. These are the groups. So a carbene will generate here. Then this N2 will remove. This N2 will get removed and giving us this. Giving us this carbene system. So what will happen? So this carbene will add up to this double bond, giving us this complex. So giving us this one. So see, this is the carbene is getting added to this double bond, giving us this. So similarly, the same type of reaction is happening here. Also a carbene will generate and it will add to this double bond, giving us a 3,6 fused bicyclic ring. So again the same question, why is not, see why the nature of the alkene is same here. Like here is also 1, 2, 3 substituted trisubstituted alkene. Here is also this is trisubstituted alkene. So why the reaction is happening here, not here? Because if it's getting added to this double bond, we will get a 3 fused bicyclic ring. But if we would get added here, then we would get a 10 member ring, a 10-3 fuse 6 member ring. So it would give a 10-3 6 minutes. You all know that above 5 and 6, the rings are, the formation of the rings are a bit difficult. So that's why this double bond will react, not this one. So here I just gave one example of asymmetric addition reaction of carbene. So here the carbene is getting generated. This is not chiral. This is not chiral. So how can we control the addition of the alkene to this double bond? This is not chiral. You can see carbene is not chiral here because just one. This is not. After this N2 elimination, this carbene will generate. Which is not at all chiral. So how can we get a chiral compound from this reaction? So here it is reported that if we use any chiral ligand along with this carbene, we may get a chiral compound. So in this case of reaction, particularly bis-oxazolene ligand has been developed by Masamune and Evans. This catalyst has been developed by Masamune and Evans. For this catalyst, both the enantiomer of the chiral ligand are available, and the reaction is amenable to a wide variety of different alkenes. So that in presence of this ligand, a wide variety of alkene may react. Like for example, they have given here very high selectively a cyclopropene was achieved using only small amount of bis-oxazolene ligand and copper triplet. The work of copper triplet is just the elimination of N2, but by addition of this ligand, this chiral ligand, we may get this type of we are getting this compound in a high enantiomeric excess. You can see this is a 99% enantiomeric excess. That is, we are getting this compound is almost 98% yield. Like 98% we are getting this enantiomer, and the another enantiomer is like is so this is a high yield enantiomerically highly rich. So by using this type of ligand, we may get this type of enantiomeric compound also. So this is just an example of application of this carbene addition reaction in asymmetric world. So this is the reaction. So let's go to some insertion reaction of carbene. Last week also I have discussed about the insertion reaction. So today I will discuss some more reaction based on this. So here you can see I have shown that from here we are getting this. So here you can see there are 7 carbons are here. So after N2 elimination, a carbene will generate and it will add up to the CH bond here. So which CH bond? See here, like almost 8 carbons are here. So 8 type of CH bonds are here. So into which CH bond it will get inserted. So from the ring stability, we can say that this carbene will insert into that CH bond, which will selectively give 5 or 6 member ring, And if there is a competition between 5 and 6 member, then most of the cases, and preferably, we are getting 5 member rings over the 6 member. Here also you can see there is a possibility of the formation of 6 member ring. There is a chance, because there is, if there is a 6 member ring, what would be the product? If it was a 6 member ring, then we would get this product. Like, as this is added to the, here the CH1, it will, if you would added the next CH of here, then we would get this type of compound. We would get this type of compound here. Then remaining CH should be, will be 4. Add 4. To be 4, giving us this type of compound. But here you can see we are getting 92%. We are getting 92%. That is almost 100%. 92% we are getting this product. That is, the 5 member ring formation is always preferable over the 6 member ring. Here I have shown another example also. Here, based on the type of the catalyst, based on the type of the rhodium catalyst, we are getting the different product as a measure. While here it is added to this CH1, and in the next one it's getting added to this CH1. So when it's getting added to this CH1, we are getting, when it's added to this CH1, we are getting this, and when it's added to this CH1, we are getting this. When it's added to this CH, when this added to, when it's added to this CH1, we are getting this. When it's getting added to this CH1, we are getting this. We are getting this. So just changing the type of the rhodium catalyst, we can get both the compound as a measure. Understood, everyone? So here, so when this carbene is getting added to this CH1, when this carbene is getting added to this CH1, this position CH1, we are getting this product, and when it's adding CH1 of this position, we are getting this product. So our next is asymmetric insertion reaction. So as similar to the addition reaction, in case of insertion reaction also we can create asymmetric, we can get asymmetric result. So here also they have used a ligand which will chiral ligand which will coordinate with the rhodium catalyst and giving us both of the compound in a 65 in a 97% enantiomeric excess. This is an anti-7% enantiomeric excess. Sorry, what is this? Sorry, we are getting these two compounds. This will be the major one and this will be the minor one. Just by using this ligand, chiral ligand, we will get we can create enantiomer selectivity in this reaction. So our next is rearrangement reaction of carbene. Last week also I have taught some example of skeletal rearrangement. Just in the last maybe 2-3 example I have shown that when that carbene is added to a aromatic ring, what happens when a carbene is added to a aromatic ring? After the addition, a skeletal rearrangement happens, giving us a expanded ring, giving us a from 6 member we'll get a 7 member ring, or first we will get a 6 3 fused ring, then it will rearrange to give a 7 member ring. So last week I discussed about that. So today we will discuss another type of rearrangement. So here the carbene is not attached, carbene is not added to a aromatic ring. Here is a different kind of reaction. In that one, carbene was getting added to aromatic ring, then rearrangement was happening. And what is happening here? So we can see the carbene with no beta hydrogen often insert into the CH bond in the molecule. However, carbenes with no beta hydrogen atoms can also undergo rearrangement reaction with alkyl and aryl group. What they are saying? That when is the alpha elimination is happening, first deprotonation, then halogen removal, so a carbene will generate. So when this type of carbene will generate, it it involves in a rearrangement where there is a aryl group is here, and our aryl group has high migratory attitude, so it tends to it can migrate easily. So when there is this type of carbene system is here and there is there is no beta hydrogen. If there is a beta hydrogen, that would get removed and giving us a alkene system, giving us a if there is a if it would H, if one of the methyl would H, if one of the methyl would H, then it would get eliminated and giving us this compound. See, I'm just writing here. If one of the methyl was H and we are getting this compound, then easily what will happen? This will remove and giving us this type of alkene system, giving us this type of alkene system. See, so but here there is no beta hydrogen is here. So what is happening? There is a rearrangement is happening. So this carbene will shift here and this aryl group will shift here and giving us this type of compound with a 66% yield, with a 66% yield. So based on another type of rearrangement is Wolf rearrangement. So this is a rearrangement, another type of rearrangement. First was the addition into aromatic ring, skeletal rearrangement. Second is this one, and the third is Wolf rearrangement. What is this? Is similar kind of rearrangement like the previous one. So what is happening here? My cursor. What is happening here? So we know that there is a negative charge. There is a negative charge can be there as the diazomethyl. So it will add to this acyl chloride is added to this acyl chloride, and chlorine will remove like normal nucleophilic substitution reaction. This chlorine group will remove and giving us this type of compound, giving us this type of this is a diazocarbonyl compound. This type of compound will generate, and when this N2 will get removed, we will get a carbene system. So here there is a high tendency to of rearrangement. What is happening? This carbene will go here, and this alkyl group will shift from here, and we will get this type of moiety. This is called ketene. This is also called ketene system. Ketene. It is also named as a ketene moiety. uh, this is also known as a ketene moiety. So this ketene moiety will generate, and as this ketene when any alcohol or water will be there, so that will again attack this carbon, and like normal nucleophilic substitution reaction, here the negative charge will, this negative charge will take one proton from and giving us this type of compound. So if we see, so this is the Wolff rearrangement. So for this reaction, normally affected by heat, photolysis, or any metal can be used, like silver metal or silver plus one metal. So the reaction is a key step of well-known reaction, that is unested method, by which we can convert a carboxylic acid into its next higher homologue. That what is homologue means one carbon will get increased. So let's discuss the unested reaction. This is one important application of Wolff rearrangement. So there's a chain extension of acyl chloride to their homologous ester known as unested reaction. So what is happening here? So here you can see normal first this there is a acid group is here. So what will happen? This acid group will get will form acyl chloride first. So it will generate first acyl chloride. I'm just writing the just drawing the main skeleton. Just I don't have pen, so this acyl chloride will generate first. All these are here. I'm just avoiding all this. So then for when we added diazomethane, we will get this type of diazocarbonyl compound. We'll get, oh sorry, here this is already written. It's a diazocarbonyl compound. This kind of diazocarbonyl compound. Then after, as in the last slide I have discussed, that silver plus one is a can be used for this type of rearrangement. So when silver plus, here this is a salt of silver plus one. So when this is added, this N2 will get removed and a carbene will generate. A carbene system will generate. Just drawing the main structure. A carbene system. A carbene system will generate, and then the Wolff rearrangement will happen. What will be the rearrangement? This will go here, and this total group will be shifted to here, and if this type of one carbon will increase. One carbon will increase. One carbon will increase, and when we added this, methanol is there, so when methanol will add up here and giving us this type of ester compound, like the just previous mechanism. Then we will get the ester compound. Understood everyone? So there it is the overall mechanism. If we see that what is happening here, just one carbon is getting increased. See, just everything will be same, just one carbon. Why everything will be same? Because during this reaction, see, when this group is getting shifted, when this bond is getting shifted from here, this bond is getting shifted from here, these are all are unaffected. So the orientation of all the groups here will be unaffected. So everything in the product, in the substrate, everything will be same, just there is a increase of one carbon atom. So this is also a similar kind of reaction. What is happening here? So first when we added KOH, you know KOH, what happens? KOH is a ester hydrolysis will happen, then giving us acid. This will give us acid. So this will give acid, and when we added this oxalyl chloride, what will happen? We will get acyl chloride. We will get acyl chloride. So first, what is happening? We are getting ester hydrolysis. We are getting ester hydrolysis. Ester ester hydrolysis. Then the next step, what is happening? Acyl chloride formation. As we know, oxalyl chloride is a chlorine source. So what will form? Acyl chloride will form. If we take the total group as an R group, then what will form? This will form. Acyl chloride will form. The next step, when this diazomethane will add, what we will get? We are getting this type of diazocarbonyl compound. After N2 element, and then when we added this silver salt, we will get the same kind of uneasted rearrangement, and it will get shifted, and by addition of methanol, we will get this type of product. And here there is a next step is there, that is they added LiLH4. We know that LiLH4 is a reducing agent. So what it will do? It will reduce the ester to alcohol. It will reduce the ester to alcohol, which is a, and this give a grandisol natural product. Get, it will just reduce ester to alcohol. See, in this of reduction reaction, the double bond is unaffected. Double bond is unaffected. As we know that LiLH4 does not reduce any double bond, any non-conjugated double bond. It will just reduce the carbonyl compound. So it will just reduce the ester to alcohol. So our next discussion is about when this type of rearrangement happens in case of cyclic diketones. So the rearrangement leads to a ring contraction. So in the previous session I have discussed when the carbene is added to an aromatic ring, what happens due to rearrangement? A ring expansion. A ring expansion happens in that case. But here, when it added to a diazoketone compound, what is happening here? Here happening a ring contraction. So this is not aromatic ring. This is a simple ring. In case of aromatic ring, there is a ring extension is happening. But here is a normal ring is so and it's not added to a ring. So the carbene is self in the ring. So this due to this rearrangement, the ring contraction will happen. So in the first example, is a small ring compound such as bicyclo 2,1,1 hexane is getting generated. So what is the mechanism here? So if I draw the I'm trying to as much I can. So after N2 elimination, we will get this carbene, and as unested method, it will go here, and this group will shift from here to here. So what we will get? We get will this get this type of ketene moiety. So when then methanol is getting added here, giving us this type of ester complex. Similarly, here the same type of reaction is happening, but the point to be noted here. See here, the carbon is marked. If in reaction, if anything is showing that it is marked, it usually means that is the isotope of the carbon. That is, it is not the carbon. It is deuterated. It is marked as a deuterated. Just in in our lab or somewhere, we just try this type of reaction just to conclude the mechanism. So by this deuterated experiment we can conclude a mechanism. So here, sorry, it's not deuterated, sorry, it's isotope. Deuterated is for hydrogen. It's an isotope of carbon. This is an isotope of carbon they use. This is a 14C. Most probably this is a 14C carbon they use. So when this type of rearrangement happening, again carbene will generate. It will go here, and this will shift here, giving us this type of moiety, and when water is added we are getting this product. So see here, this carbon is the carbon outside the ring. So what is happening? From this mechanism we can conclude, in case of Arnister reaction, the 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 reacting carbene, the carbonyl carbonyl carbon is getting out of the ring. See, it was inside the ring, but it is getting out, it's going out of the ring. Similarly, here it was the carbonyl carbon and it is going out of the ring. So there is another example, a similar kind of example. So what, this is also a ring contraction will happen. So then there will be carbene, it will go here, and this bond will shift from here, and as by the application of methanol we will get this product. So there is another example. There is a bicyclic compound, 5,4 fused compound, and there is a diazocarbonyl moiety is here. So by the application of heat, light, we will get a carbene compound. But what will be the product? If you guys can think, just think once. I will discuss this problem in the next week. Just take it as a task for, so that you can reconnect with my video or my session the last week also. So take it as a task. So it will, I have solved lots of problem already, so it will be based on this only. So if you again just go through the reactions I have shown here, you will get an idea, so that this problem you can solve easily. So try this reaction. So our next reaction is the same kind of Arnister reaction. Based on this is similar kind of reaction is happening. I am not showing the mechanism again and again. So here this again carbene will generate. It will again the carbene will generate, and this carbene will go. Sorry, what is happening? So what will happen? This carbene will, there is a bond, it will go here. This will shift it to here, and by the application of methanol we will get this product as a 84%. This is a similar reaction when this reaction started from acyl chloride. I already discussed acyl chloride in diazomethane is there. It will attack here and remove the chlorine from the system, giving us this type of diazocarbonyl compound, and by application of silver salt we will get a carbene, and which will leads to this type of compound. See, all this will be the same mechanism. If you are having any doubt, just try to solve this reaction with a pen paper by your hand, because sometimes just seeing the reaction we may think that this is so tough, or how can we get this product, it's so complicated product is here. So it's not like that. Just try to solve the reaction by using a pen or paper. I believe that you guys can solve this problem, because I already have discussed some just similar kind of problems. So you guys will be able to do this reaction. And still, if you are having any doubt or any complication regarding this, you may ask in my comment section also. I will try to discuss all those problems in the next session. The last session's video I have uploaded already in the YouTube, and I think NPTEL will provide you the link also. I have sent them also. So it is also available in YouTube. So you can search the channel by my name as a PMRF NPTEL TAship. You can go here and watch the video to get an idea if you are not getting anything. And this one will be also uploaded within 1 or 2 days. So there's a next, this is our next reaction. Here also in the similar way, there is acyl CoA is here, and this diazo this diazomethane will add here, and the chlorine will get removed, giving us this type of diazocarbonyl compound. Again, when we heat it, as we know that in case of aniston, this reaction can be done by heat, light, and silver salt. So anything is okay. So if you are seeing somewhere if you are doing some unknown problem or unknown reaction, if you are seeing there is a diazocarbonyl compound, this type of moiety is here, and there is a or silver salt or a or HNU or heat or anything, you directly think about the aniston reaction. You directly think about this aniston reaction, which will, so here it will add here the giving us this then the diagen it will get removed and giving us this compound. All this reaction I'm giving on, like I just putting on you, just try, just give a time, because if I'm solving everything here, then if I'm solving everything, it's not it just if you see the reaction only, it will not help much, I think so. As my from my experience, I can see that if you try to solve the reaction with a pen or paper, this will be, the knowledge will be inbuilt in your brain. So if you can solve anything, any problem based on this concept, it will be so much and it will be so much clear to you that you can solve any problem based on this. So here I have shown another reaction. Here also the carbene will generate, and it will shift here and it will shift here and giving us this compound. As methanol is here, so we will get a methanol ester. If there is methanol, we will get a methanol ester. If there, see here is, here there is a benzyl alcohol, so we are getting a benzyl ester. If there is water, we will get acid. Similar, just simple. If methanol will be attacked, so we will get methanol ester. If some another alcohol is that you will attack, will get ester of that one. If there is simple water, we will get acid. So this is another reaction. I will this in this one to let's solve. I'm giving you just 1 minute. Just try to solve this. I will solve this one right now. Just try to solve this. Just if you are watching this video, just try to solve it. Just give, it will just take maybe 20 seconds. Just try to solve this. don't know what happened. Sorry, I think some problem. I, I, I don't know, some problem has occurred. I was just, I was just teaching you guys, and I saw that I have got removed from that class or something. So anyhow, I will upload this video. So if anyone missed something, so go there. You can. I don't know how it happened. I was just going through the videos and also. If you guys have any, I just missed the thing, you can go there. In the last 15 minutes even, I will try to recap everything what I have taught. I just taught with 13 slides, and I don't know how much it's you guys have seen or not. So I will check once it's getting recorded or not. So this is I gave this problem to think once. I was in the I was just explaining these things. I will show once this unested reaction I was explaining. So what is happening here? I will go through once. It's like a wolf rearrangement is happening. So this type of rearrangement happens, giving us this type of ketene moiety, which will, by the addition of is alcohol, will get this type of ester. Based on this, a unested reaction was, was done. So this is I will. So this is the I was going through. So I just tried to give you this problem to solve for 1 minute. So I will show the answer. So this here again the carbene will generate. So this carbene will go here, and this bond will shift from here, and we will get this will be the so this will be our product. So this one will be our product. So when water is attacking here, so the product will be like this. So the product will be like this. So next, now I will try to discuss some named reaction involving carbene. So it is a Bamford-Stevens reaction. So in this, what happens in this reaction? When a mild base is employed, promotes the deprotonation of the acidic NH first, acidic NH first. Then the resulting salt can be heated to lose this aryl sulfonate. So it will, when it heated, this lone pair will go here and this aryl sulfonate will get removed, and to give sulfonate will get removed, and this compound is so, and this is a kind of diazo compound. So so when this compound gets generated, it will removed from the system, giving us a carbene moiety, And as there is a adjacent H is there, there's a beta hydrogen is there, so it will get removed, giving us this type of alkene moiety. Understood? So this is called Bamford-Stevens reaction. So when this can be formed by just by using ketone plus hydrogen. Ketone plus hydrogen. Tosyl hydrogen. So, tosyl hydrogen. Tosyl hydrogen. Or any hydrogen or something, will get this type of compound, and this is called Bamford-Stevens reaction. So based on this Bamford-Stevens, I have shown a problem here. So what is happening? So here after the addition of base, the similar kind of this proton will get deprotonate first, then this lone pair will shift here, and the tosyl group will get removed, and then the diazo group N2 will get removed, giving us N2 will get removed, giving us a carbene here, and there is a hydrogen. There is a two hydrogen. One is here, one is here. So we all know a hydrogen in a bridged position. Bridged position means where the two rings are joined to each other. Not bridged actually. When the two rings are joined to each other, is always not much stable. So that's why the selectively this hydrogen will get removed and giving us a double bond here, not here. Understood why not here? There is also hydrogen, but not here, because if it gets removed, the double bond, it will be a bridged position. So uh, double bond at ring junction a double bond at ring junction is not much stable. Is double bond at ring junction at ring junction not stable. Not stable. Understood? So then go to the next problem. So then next is Code-Winter reaction. This is also a named reaction where the carbene is get involved. So what is happening? There is a decomposition of the thiocarbonate leads to the formation of the alkene, possibly by the way of a concerted process or by an intermediate carbene. This required heating with, so what they are saying? This is a, this is called a thiocarbonate compound. A thionocarbonate compound. This is called a thionocarbonate compound. So by the reaction of by the reaction of triethyl phosphate on heating, we will get this type of product. But although in a milder condition we can use this one to get in a milder condition to get the product, nowadays we use this one. Usually we used to use triethyl phosphate, that is PET3, but for this one we need a high heating. But by using this one, we can carry out the reaction in just a moderate temperature. So under this mild condition, the reaction is applicable to complex and sensitive molecules containing variety of functional groups. So see here, so what is the mechanism? So here I have shown the mechanism. What is happening first? There is a thiocarbonyl compound. So this oxygen will attack here, then one chlorine will get removed, and again another oxygen will attack here, another chlorine will get removed, and giving us this type of thiocarbonate compound. So when phosphate is added to this reaction, what is happening? As phosphate has a lone pair and sulfur has a vacant d orbital, so phosphate will add to this sulfur and creating a negative charge on the carbene, and again a phosphate, there is a plus charge is generating, so again this carbon sulfur bond will get removed and giving us this type of carbene moiety, which will rearrange to get this type of product. What will happen? This type of thing will happen. This type of rearrangement will happen. By the minus of CO2, we will get this type of alkene moiety. So the next is the Code-Winter reaction. So that in this reaction, the reaction is highly stereospecific. So what does it mean by highly stereospecific? So you can see in the previous slide, for the formation of this intermediate, the formation of this intermediate, there have to be this two OH group have to be in the same plane. See, in this reaction also the two OH group is in the same plane. So the formation of this intermediate, the two OH group has to be in the same plane. So here you can see that one OH is below the ring, one OH is above the ring. So two OH are not in the same plane. So to take them in the same plane, there will be a bond rotation. There will be a bond rotation, which leads to two OH group in the same plane, and then the same reaction will happen and giving us this type of alkene. So when it will rotate, we will get this. When it will rotate, we will get this, which will react in the similar way. Which will react in the similar way to give this type of this compound. But here you can see the two OH group are already in the same plane. Both are in the above. So there is no need of bond rotation. It will just react with this one and giving us the alkene. So here the geometry is restored, but here there is a bond rotation is happening just to get the scene arrangement of two OH group. So next there is a reaction. So I will just solve this one. So there, what is the question is saying? Draw the structure of the cyclopropane intermediate and explain the formation of the cycloheptadiene in the following reaction. Explain the stereochemistry of the product by drawing an appropriate three-dimensional conformation of the transition state. So here we are just avoiding this step because it's not in that much in UG level. The pain. So for now we are just excluding this one. For now we are just excluding this one. We'll just exclude this part. Not needed for this level. So what is this? So what is happening here? So here by the reaction of rhodium plus 2 catalyst, we will get a carbene system, and this carbene will add up to the one of these double bonds. So which double bond it will add up? Because this is a electron withdrawing and this is a electron donating, so it will add up to this double bond, giving us this type of cyclopropene, and we are getting this product. So now how we are getting this one I was discussing before also, through sigmatopic reaction. 3,3 sigmatopic reaction. So how this is happening? See, this is a through sigmatopic reaction. So this one, 2. So there will be a 3,3 sigmatopic reaction. So this will move here. Here. The concerted reaction, all the bond will form and break in the same step. This is a concerted reaction. This is called 3,3 sigmatopic reaction. By this one, this is a simple reaction. One is addition, then sigmatopic reaction. We are getting this product. So our next question is this one. So I'm giving just 2 minutes. I have 30 minutes still. So I'm just thinking for 10 seconds. So let's discuss. So what will happen? This by the application of silver salt, this into this is happening. This N2 will get removed and we'll get a carbene here, and this, as before adding to the, as we know, as I have discussed in the last session, that the CH bonds, the NH bonds are weaker than that of the CH bond. So if there is any heteroatom like CH, NH or OH bond is here, so the carbene has a tendency to add to the NH bond in a faster than that of the CH bond. So what will happen? So this carbene will add it to this NH bond. Sorry, or the cursor should be in the wrong direction. So what will happen? This will add to this carbene system, giving this type of moiety. See here, the stereochemistry of this center is unaffected because it's not involving in the reaction, so this will be unaffected. So here this is the mechanism. So here you can see what is happening. So normal first unested mechanism, then then in, oh sorry, that is then here first unested reaction will happen, then instead of, as there is no alcohol or water is there, so the NH will attack. So, this is the mechanism. So what is happening? First, the N2 will get removed, giving us the carbene system. Then we will get giving us this carbene system. Then normal unested type of mechanism. This will go here. This will go here. We will get this product. We will get this product. And when as the NH group is here, as always no intramolecular reaction always preferable intermolecular, so this NH will attack here, this NH not nitrogen will attack here and giving us this. So our next reaction is this one. So it is from a previous year's reaction. So they have given this type of reaction. These are the options. So I'm just giving you 20 seconds. Just think about it. Then I will solve this one. So this was the problem. So let's solve. So this is the solution. What is happening here? Like I have discussed in the previous class, the first this this uh, carbene will add up to this alkene system. Then we will get this type of cyclopropane ring, which will then, when we added this type of oxidizing reagent, it is ruthenium chloride is an oxidizing reagent. Just for information, just remember the ruthenium chloride is an oxidizing reagent. So when it will get added, we will get this. The first it will add to the previous cyclopropane ring and it will oxidize. It is a two-step oxidizing agent, highly oxidizing. So this alcohol will be directly oxidized to the acid. So the what will be our product? So this one is our product. So this one is our product. Understood? So it's just scene addition will happen. See that both the group will be in the same position. Scene addition is happening. So our next reaction is this one. This is also from a previous year's question. So it's kind of a named reaction. This one I will discuss in the next class. So for now, just understand. I will discuss elaborately in the next class. One sec. So what is happening here? So this is the reaction. So by this one, by alpha elimination, a carbene will generated. A carbene will get generated. This carbene. So a carbene will get generated by from the alpha elimination. By this reaction, we will get this carbene. We will get this carbene. It will add to this. Then normal electrophilic addition will happen. Like it will go here, attack here, and we will get this type of reaction. After aromatization, we will get this type of compound. As in the medium, already in the medium OH minus is here, so it will remove both the Cl group, giving us this compound. We all know that a geminal diol is always too much unstable, always removes water, giving us this type of aldehyde compound. So this is the first step. After the first step, we will get this compound. So in the second step, the reaction when this type of reagent, you can see H2O2 NaOH, and there is a aldehyde group, there will be a Dakin rearrangement giving us this product. So what is the product of this? In case of Dakin rearrangement, the CHO group turns to OH. The CHO group becomes OH. I am not showing the mechanism. If you are having, if you guys have any interest, so you can say me so that I can show that in the next class or somehow. So from here to here, this is the Reimer-Tiemann reaction. This one I will discuss in the next class. So this is the next problem. Just try once. So let's solve. So this is the mechanism. So what is happening here? A carbene will generate. Similarly, a carbene will generate, and as there is an oxygen lone pair is directly available, it will add to this carbene center, giving us this type of compound. So which one is the our product? Let's see. So this one is our product. Understood, everyone? Okay. So our next reaction is this one. So this is the same kind of reaction I have just taught Code-Winter. Instead of, in case of Code-Winter, we had 2 chlorine here, but here instead of chlorine we have 2 imidazole compound. 2 imidazole moiety is here. So in the similar mechanism, in the similar way, it will give this type of intermediate. As both the OH group are in the same position, so no need to rotation, no need of rotation is, sorry. So this type of compound will generate. Then when you are adding phosphate, so what you will do, this phosphate will attack here and a negative center will generate here. Phosphate will on the sulfur. Phosphate will attack on the sulfur. The negative center will generate, and this negative center again it will remove. So our we'll get this type of moiety. Carbene, and what will this carbene will rearrange to give us this product. So what will be the product? So the everything is same. everything will be same. It will be a double bond. So this one is our product, and what is our byproduct? B means we have to show the byproducts also. So what will be our byproduct? So see, you can see here there's a 2 carbon and oxygen. So one carbon dioxide group is getting removed, and in the first step, when this phosphorus was attacking to the sulfur, after the removal of the sulfur, we are also getting this type of compound. So this one will be our first. This one will be our answer. So this is the next problem. So the options, you can try once. So this is the answer. So what is happening here? It is happening here. So first, the similar way that carbene will generate here, carbene will generate here, or then normal electrophilic addition kind of. This will go here and it will attack here, and this type of reaction will form. So what is our product? So this one is our product. So our next reaction is this one. This is our last reaction of today's session. So the structure of the reactive intermediate generated in the reaction. So we all know is by alpha elimination it will generate this. Alpha elimination it will generate this. And when there is a halogen atom in case of carbene, this will always be a singlet carbene. This will always be a singlet carbene. And in the first session, I have taught you guys that one sec. So what is so it is a singlet carbene. So this will be a singlet carbene. So in the last session, I have already taught that in case of singlet carbene, the carbene lone pair always occupy the sp2 orbital. So always occupy the sp2 orbital together. So this will be the answer. So this will be our answer. So today I am ending my session. right here. So next week we will meet again. So till now, if you guys having any doubt or anything, you can uh, up, you can ask those questions in my comment box, and also in the feedback form also. I will try to resolve those issues. So these are my these are today's session. So thank you everyone. We'll meet next. So if anyone has any doubt, I'm giving just 1 minute or 5 minutes. Just ask. If anyone having any doubt, I'm just giving 5 minutes to ask. You can. So goodbye everyone. So I'll try to upload this video within 1 to 2 days in YouTube. My YouTube channel is Chanda Devnath PMRF NPTEL TAship. You can go search here and you can go, watch my videos again. I will also upload the slides soon. The NPTEL will provide all these things. And till now, if you having any doubt, you can ask me in the next session. I will try to help you guys. So thank you. Goodbye. Good evening. Good night. Good night, everyone.